Serial correlation part 2. Serial correlation refers to the correlation among the error terms of two different time periods when there is a kind of covariance existing between them. So by serial correlation we mean that the disturbance term of the stochastic terms are interdependent on each other, and this poses the problem of self-regression or a self-correlation among each other. So this invites the problem of serial correlation or autocorrelation. So when we are defining the problem of autocorrelation, we are meaning that the error terms are related with each other, which is very much pronounced in case of a time series data or in case of a cross-sectional data also. So by the definition of the OLS assumptions under a classical linear regression model, it is seen that the covariance between the error terms is 0, where we find out expectation of uy, uj is equal to 0, where I and j are actually not equal to each other. But in the presence of autocorrelation or self-correlation, we observe that these uy and uj are dependent, and because the random effects, the disturbances, the policy effects, and many kind of unwanted incidents or observations all are affecting the disturbance term. So this gives rise to the problem of autocorrelation. So after the autocorrelation problem is being defined, it is very important to identify the sources, and accordingly we need to find out any kind of confirmation regarding the presence of the problem. So for confirmation regarding the presence of the problem, we need to highlight on the problem of detection. So any kind of data set or data series, we need to look after how the problem can be detected, and this detection refers to two kind of procedures are adopted. First, an exploration of the data series, which calls for a graphical representation, or an inferential, which calls for basically the testing. So when we go for an exponential or a kind of an exploration is being done, we go for a graphical method of detecting the problem, but there needs to be a confirmatory test, and for that we need for running the test for autocorrelation. So by the graphical method, we refer to the visualization of a correlation or a scatter plot between the error term of the current period and the error term of the previous period. So this scatter plot will give us some kind of bias or some kind of relationship or a pattern that may be existing in the diagram, or we can go for a plot across the time period. So then also we can get some resemblance of the data. So graphical method is just a pictorial representation to show the relationship between the error term of time period t and the time period t minus 1, and how are they ordered with each other. So when we go for this particular slide number 5, we observe that there are 4 quadrants in this particular diagram, or 4 zones. So we observe that residual 1 is plotted on the y-axis, and residual 1 minus 1, that is the 1 period lag value of the residual 1 series, is plotted on the x-axis. So we observe that the scatters are actually starting from zone 4, and they have a tendency to go to the zone 2 in an increasing order. So this scatter plot follows a systematic pattern, which is an increasing trend being observed. That means the autocorrelation coefficient between the error term and the past value of the error term, that is epsilon t and epsilon t minus 1, happens to be positive, which means rho is positive. So there is a presence of a degree of a positive autocorrelation among the residuals, and that is evident from this graphical representation. So from the graphical representation, some comments we can make. First of all, the residuals are showing a trend. Either this trend is explained by the factors which are certain, like deterministic factors, like for example the policy effect or the political scenario of the country. If it's a data of a country, then it's a deterministic pattern, or maybe due to the stochastic trend, that means random factors, that is any kind of global shock, any kind of currency crisis, or any kind of effect, like for example the impact of a sudden pandemic. All these comes under the random shocks which can affect this trend. So this calls for a structure of residuals we follow, and that structure is called autoregressive structure. That means error term of today's time is dependent upon the error term of the previous time period, and that is a autoregressive structure is formed. And thereby we need to calculate the autocorrelation coefficient and also the partial autocorrelation coefficient. Both needs to be computed, and which can be done or which can be visualized in terms of a graphical presentation. And after getting all these visualizations, it is necessary to go for the test. So when we go for the test, we go for a confirmatory test, we go for a hypothesis testing or an inferential testing. So after understanding the problem of autocorrelation, the detection of the problem is important using any kind of visual methods like a graphical presentation. And after the detection, we need to go for a kind of a test to understand the severity of the problem. Because for the problem diagnostics or diagnosing the problem, we need to understand the degree of autocorrelation or degree of the problem, which calls for the confirmatory test. Now we focus on the confirmatory test to actually detect the problem of autocorrelation and finally confirming the presence of the problem. So when we go for the autocorrelation test, the first very important test is Darwin-Watson test, which is called DW test most often. This is basically the most popular and the celebrated test which is developed by the statisticians, two statisticians, Darwin and Watson, and they actually compute a d-statistic to identify the problem and to explain the nature of the autocorrelation, which means whether it's a positive or a negative or any kind of autocorrelation of any degree. So this calls for a kind of the assumptions which are necessary to run the test. Because this test may not be applicable in all cases, it is based on the set of assumptions. So in this particular slide, we will focus on the assumptions when the test can be conducted. The first assumption says that the regression model includes the intercept term. That means intercept term must be there in the regression model, which actually refers to the presence of a constant term. Because this constant term is an autonomous element which may be unaffected by the time values or may be unaffected by the other factors. If it is not present, then the regression passes to the origin, but it is essential to rerun the regression including the intercept term because we need to find out the residual sum of squares. So whenever we are interested for the intercept term, it is actually incorporated in the error term, and we can see that it is having an influence on the RSS. Secondly, we need to observe that the explanatory variables happens to be non-stochastic, which means there should not be any kind of correlation between the X and the error term. That means there is a problem of endogeneity or there is a problem of interrelationship between the omitted variables and the explanatory variables. All these things must be ruled out whenever the test is applied. So Darwin-Watson test actually assumes that the independent variables are non-stochastic, and so in every repeated sampling they are obtained in fixed numbers or in fixed counts. This is the second assumption as we combine. The third assumption, which is very much important for this test, that it can only be applicable if there is an autoregression of order 1. That means today's error is dependent on the last year's error. So there should be a lag of 1 and not more than that. So if there is a lag of higher orders, then Darwin-Watson test cannot be applied. So it appears like this, that the regression model should not include lagged value of the dependent variable as one of the explanatory variable, and that means it should not be actually yt minus 1. So if I consider yt is a function of yt minus 1, then yt minus 1 comes out as a lag dependent variable. Under that case, endogeneity problem arises and Darwin-Watson cannot be applied. Similarly, there should not be any missing observations in the data, because missing observations might pose a problem in the statistical significance of the d-statistic, because degrees of freedom might be affected. So basically this one is one of the crucial assumption. Apart from that, this is also said that the error term should follow first order autoregressive structure. That means ut will be the function of ut minus 1 and not ut minus 2 and any higher order. So in case of any higher order, Darwin-Watson test will not be applied and autocorrelation coefficient will be of the order 1. Then only this test can be applied. And then the ut should be normally distributed. So this ut refers to the error term of the ut, which is dependent upon ut minus 1, which should be normally distributed. So given this set of assumptions, we can put forward the application of Darwin-Watson test. So if these assumptions are satisfied, then we can concentrate on the Darwin-Watson D statistic, which is shown in this particular slide. So we observe by the formula that Darwin-Watson D statistic stands out as summation within bracket ut hat minus 1 whole square, which is basically in the numerator, divided by summation of ut hat square. Here we observe that there is a relation between the Darwin-Watson D statistic with the autocorrelation coefficient. So actually we need to remember this expression which is mentioned in the slide as D is approximately equal to 2 within bracket 1 minus rho hat. So what is this rho hat? This rho hat is the estimated value of the autocorrelation coefficient 2 into 1 minus rho hat within bracket, and we observe that if the rho hat is 0, that means if there is 0 autocorrelation or the error terms are not related with each other, then we can see D is equal to 2. See, if we get the value of Darwin-Watson is equal to 2, then we can eventually mention that the problem of autocorrelation does not exist, and thereby there is actually the presence of OLS assumptions and OLS can be applied. So thereby D can take different values and accordingly we can comment on the acceptance or the rejection of null hypothesis. This boils down to slide number 12, which is explaining the entire region or different segments of D. First of all, we actually categorize this diagram within the limits of 0 to 4, because if we take 2 into 1 minus rows, if we take rho has to be 1, then D is 2. But if we take the autocorrelation coefficient to be minus 1 or plus 1, then accordingly we can see that it will be minimum 0 and maximum it can be 4. So it will lie within the range of 0 to 4. So we observe that we will reject H naught, which is the null hypothesis of no autocorrelation, if there is an evidence of positive autocorrelation, and we will also reject if it is an evidence of negative autocorrelation. But there are some inconclusive regions, and also we will find out that D will lie between different intervals. So here we observe in this particular slide that first if we concentrate within the range 0 and DL, where L appears to be the lower limit or the lower value, which means that autocorrelation coefficient is becoming positive, and so here we reject H naught if D lies between 0 and DL. Similarly, if we find out that the value of the D statistic lies between 4 minus DL and 4, also will do the same because of the presence of negative autocorrelation. But these two zones are inconclusive because D does not take any particular value. And again, if we come to D equals to 2, then we can understand that basically it is a presence of non-autocorrelation. So that it deviates from 2 towards 0 or deviates from 2 towards 4, then the null hypothesis gets basically rejected. So based on this, we can actually highlight upon different types of autocorrelation tests or what are the steps involved in the Darwin-Watson D statistic. So step 1, we have to run the OLS to find out the series of the residuals. So knowing the presence of the problem, in spite of that, ordinary least square regression is to be run and we get the residual series. From the residual series, we go to step 2, we calculate the D statistic applying the formula as mentioned. And after that, we are basically finding out the critical values of DL and DU and we take our decisions accordingly. So step 1 is we are running the OLS regression and we are fitting the residuals. Step 2 would be, based on the residuals, we calculate the D statistic. And after calculating the D statistic, we get the upper and the lower values, and accordingly we can go for some decisions that can be taken. So what are the decisions that we follow here as step number 4? So step number 4 is very crucial because we arrive at the decisions of either accepting or rejecting the null hypothesis. So we observe that the computed value of Darwin-Watson D statistic is D star. If it is less than the critical lower value, that is DL, then we accept that there is a positive autocorrelation of order 1. So AR stands for autocorrelation of order 1, because only for order 1 this test can be conducted. Similarly, if we see that the critical value of D star, which means the computed D statistic, is greater than 4 minus DL as shown in the diagram, then we accept the presence of negative autocorrelation. But if D lies between these two ranges, then D is actually equal to 2. So the computed value of D statistic is exactly equal to 2, which means rho is 0, and that means that the autocorrelation is not present. And finally, we have the inconclusive result when D star lies between these two ranges, lower and the upper. So we cannot comment about either we reject or we accept. So based on this, we can see the Darwin-Watson test is one of the popular tests, strong test, and based on the D statistic, based on the values of the D statistic, they can confirm the presence or the absence of the problem. However, this test has certain limitations. One of the most important limitation is the regions are inconclusive. So if the D statistic falls within the region, then Darwin-Watson will not be able to say whether the null hypothesis is accepted or rejected. So this calls for any other further methodology. Second limitation is it cannot be applied for higher order relationship. It may so happen that the pandemic of 2020, which has already affected, is affecting the error term of 2023. So 2023, any current value is affected by the disturbance of 2020, but I want to capture the correlation coefficient. I cannot apply because it is having a lag of order 3 instead of a lag of order 1. So under such case, this test cannot be applied. And thirdly, if there is a lag dependent variable which occurs in the finance data, which occurs in the investment modeling, even in the growth equation, we cannot apply the Darwin-Watson test directly. So in all these cases, we can observe the Darwin-Watson test is basically inapplicable. Another non-parametric test is not done in a very serious manner, but we can have an idea about the test which calls for von Neumann ratio test. This test is applicable mainly for the small sample when the data points is less than 30. So hardly a time series data exists for less than 30. However, if any data series has observations less than 30, we can take the first difference of variables and we can divide by the variance of x and we can see whether the null hypothesis is accepted or rejected. This test is not so popular, but this has a limitation because it is applicable only for small samples. So among this, the Darwin-Watson test is the most famous and the most done test to detect and to confirm the presence of autocorrelation. After detecting the problem of autocorrelation and also confirming the presence using the Darwin-Watson test, it is important to devise any estimation methodology whereby we can actually deal with the problem of autocorrelation. So this methodology calls for what are the estimation techniques that can be applied in the presence of autocorrelation problem. So for this purpose, first of all, we look at estimation in first difference and in levels. So whenever we are collecting any kind of time series data, whether it's a GDP or a kind of any frequency data, we need to first understand the trend of the data. So for example, if I consider a macroeconomic data, say a GDP data, then GDP data can be collected year-wise, say for 30 years or 35 years, and we find out that there is a kind of a trend observed in the data after plotting it. That is a graphical visualization. After that, we need to find out that what type of trend it is. So if it is find out that the trend is due to any deterministic factor or can be stochastic factor, so we need to find out the estimation process for this. So here we observe that the variable y, if it is a GDP data, depends upon the variable in the previous period, and accordingly we can see yt is a function of yt minus 1. So this yt function of yt minus 1 will actually refer to a kind of autocorrelation problem, because the error terms are also dependent on each other. So we say equation in the first difference or in the levels. So whenever we refer to equation in the levels, we consider the GDP data as it is, and in the levels we have the problem of all these trends. These are indications of non-stationarity. So regarding the sources of autocorrelation, we have highlighted that non-stationarity is one of the source of autocorrelation problem. So this data is showing a kind of a trend, so that we can see that the data is non-stationary, which means the mean and the variance are keeping on changing. So if it is keeping on changing, then the autocorrelation coefficient also will be positive or negative, and that will confirm the presence of the problem. So one of the very much easier way outs to actually diagnose the problem is to take the first difference. That means we divide yt from the first difference yt minus 1, and we get an equation in the first difference. So equation in the first difference can be estimated, equation in the levels is existing, and thereby we can go for an initial treatment of this problem. But the problem is not so simple to get diagnosed so easily. So we need to check further a confirmatory test, as it is done all the way, which refers as checking the unit root. Unit root means that whenever we are saying that ut is dependent on ut minus 1 and there is a autocorrelation coefficient rho, we means that whether rho is equal to 1, unit means 1, or it is not equal to 1. So if it is equal to 1, definitely ut is dependent on ut minus 1, because that is how the relationship holds. And if it is not equal to 1, then it means that there is no autocorrelation problem. So if the autocorrelation coefficient happens to be 1, then we can see that unit root problem is existing, and accordingly the proper test can be devised. And finally, after detecting the unit root problem, we want to get rid of that, and getting rid of that makes the equation to take in the first difference, and thereby we can apply the estimation technique. So for the estimation technique, what we follow, first of all we plot the data, we identify whether any kind of trend is there by visualization, and then we consider the data in the levels as it is. We conduct a test for that, that is called unit root test. And if the problem is existing, we take the data in the first difference, and again we conduct the unit root test, and finally we carry on the estimation procedure. So this calls for this particular slide, where we find out that the data in the levels or the data in the first difference. If we refer to the first equation, we observe that yt equals to beta 1 plus beta 2 xt plus ut. What does it mean? It means yt is dependent upon xt, both are current periods. So current value of yt is dependent upon the current value of xt, and it is basically a kind of a bivariate framework, where we are basically moving from univariate to bivariate analysis. So yt regressed on xt, and definitely the OLS residuals are obtained. But in the second equation, we observe that the lagged value of yt is dependent upon the lagged value of xt, such that yt minus 1 equals to beta 1 plus beta 2 xt minus 1 plus ut minus 1. So on the basis of this, if we do the difference between yt and yt minus 1, we are left with delta yt, which means it is capturing the changes in yt of the two time periods. Beta 1s are getting cancelled out, and beta 2 delta xt as it is plus vt. So what is this vt? This vt shows the difference between the current error term and the error term of the previous period. So ut minus 1. So this equation is called the first difference form, where yt is subtracted from its own one period lag value, and this basically refers to a dynamic regression model. So if this equation is considered as a first difference form, and we can confirm that there is no kind of unit root problem, that is autocorrelation coefficient is 0, we can apply OLS to this difference form. Otherwise, in the original level forms, whether this one or this one, where yt is a function of xt or yt minus 1 is a function of xt minus 1, we cannot apply OLS directly because they might be giving to the problem of autocorrelation. So we can observe that the error term in the first equation is not autocorrelated, but the second equation is definitely autocorrelated. So by taking the first difference, we can go for our proper estimation techniques. So the major way out is by taking the difference from the lagged period, we take a variable in a dynamic form, that is delta yt or delta xt, and thereby the proper estimations can be carried out. This is one of the ways to get rid of the problem of autocorrelation. So in this particular slide, if we sum up, we come up to these three important concepts. Firstly, we discuss on the concept of autocorrelation, which is basically the serial correlation among the errors, how they are self-correlated with each other. Then we go for the test of autocorrelation, which means we have the graphical as well as the confirmatory test. Graphically, we can plot the residuals and check the scatter plots. We can get an idea of the autocorrelation coefficient, both partial and ACF. And finally, we can go for the unit root test. And then we can go for detecting the problem in an inferential testing, which calls for Durbin-Watson d-statistic. So Durbin-Watson d-statistic value ranges between 0 to 4, and it has a relation with autocorrelation coefficient, where d is approximately equal to 2 into 1 minus rho hat, which means if the rho hat is 0, then the d will be 2. So if we get any value near to 2, then we can say that the null hypothesis of no autocorrelation can be accepted. But if d is closer to 0 or closer to 4, which are the extreme values, then definitely autocorrelation exists. But there can also be inconclusive regions regarding this. Another non-parametric test is also being conducted, which is only for small samples, von Neumann ratio test. And finally, the estimation can be done even in the presence of autocorrelation if we go for the transformation of the variables. That means from the levels, if we go for, in case of the first difference, we can go for the estimation procedure and we can apply the OLS. So thereby the autocorrelation problem can be rectified. So autocorrelation problem is pronounced in the time series data. It calls for detection. It calls for confirmatory test. And finally, it calls for the proper estimation procedure.